This is Dylan Sieverts going over Chapter 17 homework. For number 1, it's basically the flywheel with the punch that rotates at 300 revolutions per minute. And basically, we need to use the conservation of energy to find our T1, our kinetic energy at point 1 and point 2. From there, we can do the conservation of energy formula and plug in our T1 and T2 values. In order to find T1 and T2, we do have to find the moment of inertia, and it does give us our revolutions per minute, which is our angular velocity. So we just convert that to radians per second. And from that point, we're able to find inertia. And then for part B, it asks for the number of revolutions. And from that, we basically just use our 10 pi radians per second, and then the work done, and the amount of foot-pounds, and then we're able to find our unknown, which is radians, or revolutions, theta. And then 2, the slender rod, it wants us to determine the angular velocity at different positions. So at position 1, we need to find our kinetic and potential energy, and position 2, we also do. And I drew it over here to the left, and from that we put everything in terms of just L, since it gives us that. We don't necessarily have our radius, and we take our center of rotation, and then we're able to do a sum of forces and get our omega here in terms of gravity and the length of the bar. Part B, it asks us to solve part A with just certain components, and so then we're able to solve for a y with the formula that we came up with. Number 3, I went over this one with you in office hours. So basically, we have 3 different positions. Position 1 right here, 2 there, 3 there. And we need to find our potential and kinetic energy at each point. Point 2 is a little more complicated because we have that 30 degree angle. And so we do have to account for that with our center of mass, mg, pointing down for each rod. And then for our moment of inertia, we basically just combine that into make this just one figure or one bar. So that made it a lot easier when we were finding the moment of inertia, and we had to plug it in. And we know that when it's at 90 degrees, our potential energy is something, but we don't have any kinetic energy. And then we're able to do a sum of forces and find our omega. And there's a lot of canceling that's done there. Number 4, the bolt located is tightened, and it wants us to find the angular velocity of the wheel. So basically we would use the formula I equals mk squared, and we would resolve that or manipulate it and plug in our moment of inertia, and it does give us the radius of gyration, and we're able to plug that in for our K and solve for our mass. Once we find our mass, then we're able to solve for I omega by F equals ma, or F equals I omega. And let's see. Yes, so that's our total moment. Number 5. This one, we basically have our linear and our rotational kinetic diagrams just combined here. We know that there is a force from the ground as well. And so in order to find that, we needed to find our total forces and then do our sum of our moments about the middle point, G. And that was able to give us our omega. And it didn't give us any values, so it just wanted it in terms of variables. Part B, we would just take our time equation and solve for t, because we know that t equals mv over f, and then we plug in all of the known values that we have. And moving on to number 6, we also went over this one in office hours. So we can think of this as 2 different positions when this middle plate or piece of wood is vertical and when it's horizontal. So the first part of our moment of inertia, 1/2 mr squared, stays the same for both because that's the bottom disk rotating about the x-axis. However, when it's vertical, our moment of inertia is different because it's rotating about a different axis. And so that is 1/4 mr squared instead of 1/2. And it's only half of the disk, so we take into account that for 1/2 m, the mass of the full disk there. For our horizontal, it's the same idea, but that plate is flipped down, so again, it's rotating about a different axis. And so that is the 1/2 mr squared. We replace the mass with 1/2 of the mass. And then from there, we are able to set them equal to each other and solve for our angular velocity. And number 7. This one was a little bit harder for me to understand. But basically the bullet, I drew all of my sum of forces over here in a linear diagram, and then to the right that equals my rotational or angular velocity and momentum. So we know that there's a force from the bullet, we know that there's a force of the wheel, there's friction, and there's a normal force. So we do sum of forces to find our velocity in terms of mass and v. Then we can do our sum of moments to find our omega in terms of our radius and our mass. Part B, it wants us to find the linear velocity, so we just have to convert all of our components like I omega to v over r for our velocity. That's what omega equals. And then solve for v. and that is it. Number 8, we have to know our moment of inertia for a thin, slender rod, which I have there. And it's all in gray, but I did draw my linear diagram here and my rotational diagram together with all of the forces acting on it. And basically it's just from before he jumps to after he jumps, point 1 to point 2. And basically we are determining the height that the other person will go if this person jumps down on this, assuming there's no bend or anything in the plank or any of those technical things. We can do our sum of our moments to find our omega, and then basically convert that to our a linear velocity. It does give us the weight and the height of where he jumps from. So that was helpful and made it much easier to set the problem up. But basically just our sum of moments, then convert that into linear after we found our omega. And that is it.